My video device seems to be going in and out, so I kind of got interrupted at the end of that last clip, but I can pick up where I was. If we imagine that we take a piece of paper, first of all, we could fit a plane to these points, but of course that plane wouldn't be flat here. Well, if we flatten this part out, the paper will curve downward here, curve downward here. If we want to accommodate this point as well, then we can fasten the paper here and here. If the paper is reasonably flexible, we can then lift up this end so that the paper curves upward to get to this point. I would show you that, but the video device won't accommodate it if I try to put a piece of paper up there. In the first place, you're not going to have very good perspective on it. In the second place, the camera's just going to blur out. It's not going to be able to autofocus, and I don't have any other option with this camera. So we won't be able to do that, at least on this clip. But we see that it's certainly possible to have a downward curvature as we go in this direction, a downward curvature as we go in this direction, and an upward curvature as we go in this direction. Now the only way for that to happen, for fx to equal 0 at this point, and still for f to change in the negative direction when we get to this point, I won't say the only way, but what we would generally expect in this case, if we're curving downward, that means that fx is decreasing. The slope of the graph that we get if we cut the surface with our plane parallel to the xz plane, that curve is going to have a decreasing slope, which means that we have a decreasing value of fx, and of course the decreasing value of fx means that the second derivative of f with respect to x is negative. Same thing in this direction. We have a decreasing slope, which implies, and so forth, and implies that fyy is negative. We also expect that fx is less than 0, except at this point. So we'll say fx is less than 0 along the path. fx is 0, fx is decreasing, fx is less than 0, fx is decreasing, so fxx is less than 0. And up here we also expect that fy is less than 0 along this part of the path. However, for the function to increase as we move in this direction, our differential has to be positive, which means that somehow our fx and or our fy will be increasing as we move from here to here. This means that fx has to be positive here. And so does fy. Actually, I overstated that. There could be all kinds of fluctuations and undulations between here and here, but let's just make assumptions that we're not moving far enough for anything weird to happen, that the trends simply go as we would expect them to do in the simplest possible case that models this situation. That is, as we move in this direction, everything just curves upward, and it should then be clear that as you move in this direction, from any point along this curve, that fx and fy would be positive. We would then conclude that as we move in this direction, fx, since it goes from negative to positive, is increasing. And as we move in this direction, fy, since it goes from negative here to positive here, is also increasing. So that fx is increasing as y increases, and fy is increasing as x increases. If we take this statement here, fy is increasing as x increases, that means the change in the value of fy over delta x has to be greater than 0. If we take the limit of the change in fy divided by the change in x, that equals, and I'm going to assert this when we do rigorous proofs of all this, we'll make it more specific, but what's the limit as delta x goes to 0 of delta fy over delta x? That is the derivative with respect to x of fy. And if we follow our subscript notation, that means this is fy x, the x derivative of fy, and we simply write that as fyx. This derivative evaluated at this point in this situation will be positive. That is, as we move in the y direction, in the x direction, fy has to be increasing. Completely analogous argument here tells us that, well, fx increasing means delta f increasing as y increases means delta x, f over delta y is positive. And without writing out the details, that means fxy is positive. So we can say that fyx is positive through this region, and fxy is positive through this region. Now, our x derivative and our y derivative are both driving the value of the function down as we move away from this point. Our xy or yx derivative, and they're equal, is tending to move it up. Which one wins? In this case, we see that the fxy derivative or fyx derivative is big enough to overcome the downward push of the derivatives in this direction. But it's certainly possible that there could be a tendency for fx and fy to both increase as we move in this direction and this direction respectively, but not enough to overcome the downward push of the x and the y derivatives themselves. Thinking again of a piece of paper or a flexible sheet that's curving down as we move this way and down as we move this way. Okay, so we have a kind of a peak here if we look in these directions. That piece of paper could easily curve down in this way, but not quite as much, so that fxy would be positive, but not big enough to raise this point above these two. Or we could raise it high enough and the fyx derivative would then be large enough to overcome that tendency. So we'll make the statement, if fxy, which is equal to fyx, is big enough compared to fx and fy, then we can have the saddle point as described. We'll go on in the next clip to be a little more specific.